In 1897, G. Thomson discovered the electron by experimenting with the Roux or cathode ray tube. He demonstrated that cathode rays were negatively charged. But how do you view an electron? Is it a particle or a wave? Let the battle of ideas begin. Battle on the true nature of light. Isaac Newton (1643 to 1727) viewed that light consists of streams of particles known as corpuscles which light source emits. Christian Huygens (1629 to 1695) believed that light consists of waves. Here, there are two studies, Isaac Newton and Christian Huygens. Their studies have big difference because Isaac Newton believed that light consumes of particles or corpuscles, and Christian Huygens believed that light consists of waves. The battle of ideas must commence in experimental approach in which science is anchored on. Below is just a brief list of their findings based on their experiments. Can you add more on the list of ideas that belong to both Newton and Huygens? Feel free to add it in your own time after you have done doing the research in this topic. Newton and Huygens held conflicting ideas about light. Here, Newton believed in the particle theory of light, while Huygens proposed the wave of theory. Newton conducted experiments on color and invented the reflecting telescope. Huygens developed the first theory on wave propagation. Thomas Young (1773 to 1829), British physician and physicist, he established the principle of interference of light and atomicity. Early in life, he proved beyond doubt that light is a wave. Young did not just establish the wave nature of light, but contributed the many other aspects of physics or, as we could call it now, material science. Young modulus, for example, is named after him for good reason. Moreover, he was also instrumental in discrediting hydrolytic and other forgotten scripts.
The de Broglie wavelength relates to a particle's wave-like behavior, while its momentum relates to its particle-like behavior. Planck's constant links the energy of a photon to the frequency of its wave.
Sample problem 1. If you compute for the de Broglie wavelength of a 1,200 kilogram beaker that moves at 10 meters per second, you will get lambda equals h divided by p equals 6.626 times 10 to the power of 34 gm divided by 1,200 kilograms times 10 meter per second equals 5.53 times 10 to the power of negative 38 meters.
This wavelength is too small that it can no longer be observed, and cannot be bent even when it encounters an opening. This is true with other microscopic objects. However, for microscopic particles like electrons and wavelengths are also very small but have the same size as the interatomic spacing in crystal solids. Sample problem 2. What is the wavelength of an electron moving at 5.31 times 10 to the power of 6 millimeter per second? Mass of electron 9.11 times 10 negative to the power of 31 kilogram. H 6.626 times 10 to the power of 34 Js. H over mv equals 6.626 times 10 negative to the power of 34 Js over 9.11 times 10 negative to the power of 31 kilogram. 5.31 times 10 to the power of 6 millimeter per second equals 1.37 times 10 negative millimeter to the power of 10 millimeter. The Wiesen and Germer experiment. In 1927, American physicists Clinton Davison and Cluster Germer tried to verify a prediction of classical physics that scattered electrons will appear from all directions with little dependence on their intensity, on scattering angle, and the energy of the primary beam. They expected that because of the small size of the electrons, they would still be experiencing diffuse reflection even if they hit a smooth surface like that of a crystal. They found nothing significant in the experiment until their setup was broken. When air accidentally entered the setup, the nickel was oxidized. To decrease the oxide in the pure nickel, extreme heat was applied to the nickel and was used again to continue the experiment. After bombarding the recrystallized nickel with a beam of electrons, they observed that the intensity of the scattered beam was at the maximum at 50 degrees. They noted that this peak in the intensity is where constructive interference occurs. Recrystallizing the nickel made small holes in the crystal which served as a diffraction grating. A, dif- a diffraction grating is an optical device made of glass or metal with a band of equidistant parallel lines. When a wave encounters a diffraction grating, it bends or diffracts.
In the experiment of Davison and Germers, the beam of electrons that pass through several small holes was diffracted. This diffraction of electrons shows one of the properties of a wave. Waves that come from different openings of diffraction gratings, which are the small holes in the crystallized nickel, meet and form interference patterns. Interference is a process where two waves meet. Wave can add up, interfere constructively. They can also interfere destructively when they cancel each other. In the electrons exhibit only the behavior of particle, they would produce a pattern of two bands on a screen after passing through a double-slit barrier as shown in the diagram below. However, electrons also behave like waves and produce an interference pattern of bright and dark fringes, as shown in the experiment by Davison and Germer, and other succeeding experiments using modern setups. It took scientists a long time to reconcile the dual nature of light, which lead to the idea of the duality of matter. To further see in evidence of this concept, try to observe the smoke coming from a barbecue grill. From a distance, you will see a wave flow of smoke going up, but look closely into it. What do you see? Does your observation tell something about the dual nature of matter? For example, when electrons pass through a double-slit barrier, they exhibit wave-like behavior and create an interference pattern of bright and dark fringes. This behavior is observed in experiments like division and Germer's, demonstrating the dual nature of electrons as both particles and waves.